Hello everyone, I'm Thinking Tree and it's been a while since I made a video, so I just decided to share a topic that I recently studied. I did not really dive into this topic because I only needed this for my supplementary information, so it wasn't like a primary topic to study, so I just studied for fun and also additional information. But I think this concept is really interesting and also helped me a lot to understand what modular arithmetic is. So I also wanted to share it with everyone. I believe there are many of you who might have made the same mistake in school. As a freshman myself, sometimes it's really tempting to just say that this is true. Like for example, in a simple algebra, when we have to like compute this one, it's really painful. So it's just really tempting to say that this is equal to this one. Oh, sorry. This is equal to this, which is obviously false. However, I will not say that this condition is entirely false. If we add one more condition, it is true. So a plus b to the power of p, where p is um, any prime number and a and b, they're any integers. This could be true. Or I will say this is always true in mod p. So we should say this congruent. Oh, I'm going to explain what mod is soon because we need that to uh, show the proof for the freshman stream. So let's get into it. So modular arithmetic, it is also called as clock arithmetic, and you will see why it's called in like that way. Because I'm not an expert in number theory, I also don't understand fully of what modular arithmetic is, but I'm going to just share very simply what I know. So we have a typical clock, and I think most of you will be familiar with saying that 1 p.m. is same as 13 o'clock. So sometimes in a digital clock, they sometimes say this, but we know that this is same as 1 p.m. So it's 12 a.m. right now, and we add one more hour, it becomes 1 a.m. and so on. And after 11 a.m., it's supposed to be 12 p.m. And then after 12 p.m., it's supposed to be 1 p.m. However, we could also say it as 12 plus 1 or 13 o'clock. And so it's 14 o'clock here, and it's 15 o'clock here, and 16, 17, and so on. However, mathematicians, they wonder, what if we could expand more from here? So we know that it's 22 in 10 p.m., 23 in 11 p.m., and 24 in 12 p.m. However, if we go on to next day, so it's like tomorrow, we add one more, so we get 25, and 26, 27, 28, and so on. And in this case, in this clock with 12 numbers, 1, 13, and 25, they're the same. 12 and 24, they are the same. So in this case, 2, 14, and 26, they are also the same. 3, 15, 27, they are also same. And we have much more same number, so we can say that 1 is congruent to 13, or we could just say mod 12. So in a clock with 12 numbers, 1 is congruent to 1. However, it is also congruent to 13 in a clock with 12 numbers. It's also congruent with 25. It's also congruent to 37. We just add 12. It's also congruent to 49, and so on. So this is just basic idea of using modular system, and we are going to use this property to prove the freshman string. So when we generalize it, we can say that A is congruent to A plus n times k in mod k. So n and k, they are all integers. I'll say natural numbers. N and k, n can be, so a and n are integers, and k is a natural number. So this is the general idea of the modular arithmetic. I was not able to explain like more, but it's okay because that's all we need for the proof. And there's one more thing that we need to know. So there is a thing called binomial expansion. So what this is saying is that a plus b, and a and b are any integers, and n is any natural number, is equal to the sum of all this I think it was this one. Yes, it's this one. So this might look scary if you're not familiar with the notation sigma or the sum notation, but I will just break it down right now. So basically what this is saying that also this is indicating combination. So what this is saying that is that I'm going to represent this one without using, I think it's k from, it's from k equals 0. So when I expand this term, I get nc0 times a to the n times b to the 0 plus nc1 times a to the n minus 1 b to the 1 plus dot 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 plus ncn minus 1 a times b to the n minus 1 plus ncn to the 0 times b to the n. So this is what you get after expanding. And if you need more explanation, it's very simple. So in a thing called a Pascal's triangle, there's a very interesting behavior of this triangle. So this is the coefficients of a plus b to the n, and n, it is representing the layers in this case. So when n is, so this is at n equals 0, so n equals 0 here, n equals 1 here, n equals 2, and these are the coefficients of a and b, or with terms formed with a and b. So when n is equal to 0, all we get is 1. And when n is equal to 1, so a plus b to the power of 1 is a plus b. The coefficient here is 1, here is 1. So that's what we get, 1 and 1. And when a plus b, when we square it, we get a squared plus 2ab plus b squared. We get 1, 2, and 1. We get 1, 2, and 1. It's very interesting. When we cube it, it's same. So we get a cubed plus 3 times a squared b plus 3 times ab squared plus b cubed. And it's always true. Also, we could represent the same triangle in a different way. So we get 0c0, 1c0, 1c1, 2c0, 2c1, 2c0, and so on. You'll recognize that the numbers here, it's 2 here. So you recognize that the numbers, they're just the same triangle but in different form. It's too much to explain this concept in here. So what you all need to know is when n is equal to 0, these explains the coefficients of the terms formed with a or b. So let's start our proof. So we call that a and b, they're integers, and p is any prime number. It always works. First of all, what I want to do here is I want to expand a plus b to the power of p. So using binomial expansion, we know that this is equal to the sum a to the 0, b to the p. So this is what we get when we expand this one. There is an interesting thing about our coefficients. So let's observe our coefficients. So what it is saying is that for both integer n and r, we are going to choose r items from total of n items. So what are the total possible cases of choosing r items from n items? So if we have 2C1, then we are saying that we have 2 items. What is the total number of cases of choosing 1 item? So the first case is choosing this one, and the second case is choosing this one. So we only have 2 choices. So the answer for this is 2. So this is just basically what combination is. So because we know that combination and the number of choices, it is integer, we know that n and r and n, they are all a subset of, I will just say natural number. They're all subsets of natural number. And from here, we could continue. So let's just change from it to PCR. In this case, P is greater than P is greater than R in this case. So we know that this is equal to P minus R factorial. We know that this is true. And we also know that P is a prime number and R is any integer. So it is evident that P is greater than P minus R. Of course, because R is a natural number, and this is just true. And we also know that P is greater than R. Then when we write the numerator, we get P times P minus 1 times P minus 2 dot, we get 2 times 1 all over P minus R factorial times all over we get P minus R factorial. Now because we know that this thing is true, so we know that P is greater than P minus R, and we know that P is also a prime. So that means we do not have P here. So we know that P minus R does not divide P. And also, R factorial does not divide P because P is a prime number. Oh, then what's going on with the P here? It's just there. So we can say that this is equal to Pk times any integer k, or any natural number k. So we know that this thing is a factor, is a multiple. So we know that this thing is a multiple of P because P here was not able to be cancelled by P minus R factorial and R factorial. But recall this thing is same as this one. So this thing is a factor of P. And they are all the same. So we just proved that PCR is a multiple of P. That was our lemma. But our condition here is that P is greater than R. So in this case, this is true. Let's get back to the binomial expansion right here. If P is greater than R, and they are all greater than 0, they are all greater than 0. So P and R, they are both greater than 0, and P is greater than R, then we can know that we can do a very interesting thing here. So I will just rewrite this. So we know that this is true because this thing and this thing, they're the same. So we're just saying that in a clock with p numbers, the same numbers are. And also we know that from our lemma, we know that PCR is a multiple of P if PCR, I mean P and R are greater than 0 and P is also greater than R. That means this thing, this thing and any terms in between, they are all multiple of P. That means when n is a negative number, we can keep subtracting k from A, and they will always be the same. So I'm going to use that property here. So I'm going to subtract p's. If I keep subtracting p, all our multiples of p, which are these ones, they will all disappear. So what we have here is this one, mod p. But recall PC0 is equal to 1 and PCP is equal to 1. Oh, it was just. So we get a to the p plus, because they are 1, this is 1, this is also 1, b to the p mod p. We proved it. I think this idea is really interesting for me because it really helped me understand what modular arithmetic is, because when I studied problems involving mods, I thought it was only related to remainders, not the clock itself. So this proof and the problem was able to help me understand more about clock arithmetic. So this was it about the freshman stream. I hope everyone enjoyed this video. Then see you in the next video. Thank you.